Hello everyone. In today's lecture, we'll learn about our third software experiment, which is computation of probability of bit error for coherent ASK, FSK and PSK. So the aim is, as stated above only, to compute probability of error for coherent ASK, FSK and PSK for an AWGN channel and compare them with their performance curves. Software used is MATLAB 2018A, or you can use MATLAB 2013 onwards, whatever the version you have. What is bit error rate? That we need to understand first. So bit errors are the erroneous bits received at the receiver end as compared to the transmitted bits. So it is usually measured as a ratio. For example, if 5-bit errors occur in 1 million of transferred bits, the bit error is 5 by million, which is 5 into 10 to the power minus 6. This is the bit error. So now the next question arises, what is the requirement of measuring this bit error rate? It is the measure of quality of transmitting device, the receiver and the transmission path and its environment. So based on this measurement, we are going to consider which modulation technique is best for our particular application, ASK, FSK or PSK or QPSK, that we are going to do. Correct? So let us first go through the equations what we have for bit error rates for different signaling schemes. First one is ASK bit error rate is given by the Q function. The equivalent complementary error function is 1 by 2 ERFC of square root of EB by 4 N naught, whereas PSK bit error rate is 1 by 2 ERFC of square root of EB by N naught. FSK bit error rate is 1 by 2 ERFC of square root of EB by 2 N naught. If we plot these values of bit errors against the signal to noise ratio, what is this EB by N naught? It is nothing but signal to noise ratio. Varying this signal to noise ratio over different values, we can get the change of bit error rate and we can plot that. And then we will compare the same with the different schemes. Correct? So to do that, first thing we need to understand that SNR of signals is usually represented in decibel scale. So it has to be converted to linear scale for simulating the bit error rates of different schemes. EB by N naught in decibels is given as 10 log EB by N naught to the base 10. So if we take this 10 on the LHS, it will become like this, and then we can simplify it to have EB by N naught is equal to 10 to the power EB by N naught in decibels by 10. So we use this equation to simulate the BER of different schemes. This is the code. So let us directly go into the MATLAB and analyze what is this code all about. As you can see, this is code for BER computations for ASK, PSK and FSK. This should have been FSK, okay. The first line says that, so signal to noise ratio in decibels varying from 0 to 20. That is SNR in decibels is 0 decibels, 1 decibels, 2 decibels, likewise up to 20 decibels. Then according to the already derived formula, what we'll do, EB by N naught in linear scale will convert this decibel scale values. For each of this value, we will have a EB by N naught linear scale value. So we will use this EB by N naught value to calculate the probability of error or bit error rate for BPSK, BFSK and BASK. And there is a inbuilt function ERFC, that is complementary error function, which is already there in the MATLAB that we can use, which is 0.5, 1 by 2 is 0.5 multiplied by ERFC of square root of EB by N naught, square root of EB by N naught by 2 for BFSK, and for BASK it is 1 by 2 ERFC of square root of EB by N0 by 4 as already stated. So this is now calculated for every value of EB by N0 in decibels. Okay, we have converted into linear scale and we have calculated all the bit error rates. Now we need to plot them. For that, we use a semilog graph. So it is the function which we are using is semilogy, where EB N0 dB will be our x-axis. Then the y-axis will be having BASK, BPSK, and BFSK variations. Okay. Coming to the next line, we use the legend function so as to indicate which curve belongs to what particular scheme. Then X label is EB and not in decibels. So it is 1 decibel, 2 decibel. In that way, it is linear only. Though we say it as decibel, the decibel values are linear 1, 2, 3, 4 like that. Then Y label is bit error rate and with grid on. Okay, I hope you have understood the program now. Let us save and run this program. And we can see there is a graph which is showing 3 different curves. One is related to BASK, another one is BPSK, another one is BFSK. So now, what is the inference we can draw from this set of curves? Where as the EB by N0 go on increasing, the bit error rate go on decreasing. That means if you have 20 decibels as your signal to noise ratio, that is very good or high signal to noise ratio, then 10 to the power minus 45, you cannot imagine also how much small this bit error rate. Similarly, at the same time, for the same 20 decibels, you can see it is around 10 to the power minus 24 for the BFSK signal, and it is 10 to the power minus 12 or minus 13 in between that for the same 20 decibels. So you can imagine what kind of errors we can have if we use BASK, BFSK, and BPSK. This equation is same for QPSK also. So QPSK and BPSK in coherent detection have the same kind of bit error rate, and the bit error rate is lowest for this phase shift keying techniques than compared to BFSK, and BFSK is having a lower bit error rate as compared to BASK. So that is what we can draw. So this is about the coherent BASK, BPSK, and BFSK. If we can generate the non-coherent BASK, BPSK, which is DPSK, and BFSK, non-coherent type, then we can compare that performance with these particular curves. We can observe there that coherent schemes are having lower bit error rate as compared to the non-coherent scheme. Okay, but this that is out of the context of our experiment, so we are not going to deal with that. But you should be knowing this. The BPSK coherent detection is the best compared to BFSK coherent. Then BFSK is better than the BASK, and these coherent schemes are better in their performance, the bit error rate performance, as compared to the non-coherent DPSK scheme or non-coherent FSK scheme. So that's all about the probability of error computations for ASK, PSK, and FSK and their performance analysis. Okay, I hope you have understood the concept. Also, you are now more clear with the different modulation techniques. Thanks for watching.